This is Unit 5, Lessons 3 and 4 practice problems. Which expression is equal to 4 to the 0 power times 4 squared? What you need to know is that when we multiply the same base number, we add the exponents together. So this becomes 4 to the 0 plus 2, which equals 4 squared, and 4 squared equals 16. So C is the correct answer. If you wanted to verify, anything to the power of 0 is 1. So 4 to the 0 power equals 1, and 4 squared equals 16. So if we did 1 times 16, we would still get 16. A bee population is measured each week and the results are plotted on the graph. Number 1, what is the bee population when it is first measured? We can find that right here at the y-intercept, and that means the bee population is originally 500. Number 2, is the bee population growing by the same factor each week? Explain how you know. Remember that a factor is what you multiply by each time. So from the initial measurement to 1 week, we went from 500 to 1,000. So that would be times 2. Then between weeks 1 and 2, we went from 1,000 to 2,000. That also is times 2. And then between weeks 2 and 3, we went from 2,000 to 4,000. And again, that is times 2. So, yes, the factor is 2 each week. And number 3, what is an equation that models the bee population B W weeks after it is first measured? So if I want the bee population, then B of W equals the initial population of 500 times 2 to the power of W. This tells me I'm going to double it the number of times as weeks pass, and then I'm going to multiply by 500. So when we tried this, if we said 0, then 2 to the 0 is 1, and 1 times 500 is 500. If we said 1, 2 to the first power is 2, and 2 times 500 is 1,000. And that's what we have. If we substitute 2 in for W, 2 squared is 4, and 4 times 500 is 2,000, which is our value. And finally, if we substituted in 3, 2 cubed is 8, and 8 times 500 is 4,000. This is an exponential function. These equal the y-intercept times our factor to the power of x. A bond is initially bought for $250. It doubles in value every decade. Number one, complete the table. So we know that the original value is 250. When we double it the first time, it becomes 500. We double it again, it becomes 1,000. And we double it a third time, it becomes 2,000. When we're trying to find this out for an unknown value of decades, remember that we start with our original amount, 250, times our factor, which is 2 because we're doubling it, to the power of d. Number 2. How many decades does it take before the bond is worth more than $10,000? Well, we could continue trying this. 4 decades, it would be worth 4,000. 5 decades, it would be worth 8,000. And finally, after 6 decades, it would be worth 16,000. So it would take 6 decades to be worth more than $10,000. And number 3, write an equation relating V, the value of the bond, to D, the number of decades since the bond was bought. So for this, we're taking the bottom table entry and we're just turning it into an equation. We can say V of D equals 250 times the factor of 2 to the power of d decades. A sea turtle population, P, is modeled by the equation P equals 400 times 5 over 4 to the power of y, where y is the number of years since the population was first measured. Number 1. How many turtles are in the population when it is first measured? Where do you see this in the equation? The population when it is first measured is 400 turtles. And I see that right here as the standalone number in the equation. Number 2. Is the population increasing or decreasing? How can you tell from the equation? The population is increasing, and I know by looking at the factor. The factor is 5 over 4, which is greater than 1. It's equal to 1.2. So it's increasing because the factor is greater than 1. And number 3, when will the turtle population reach 700? Explain how you know. So we know that after 0 years, it equals 400. That's the initial population. After 1 year, that equals 400 times 5 over 4 to the first power, which equals 400 times 1.2 and 400 times 1.2 equals 480. Next, we can try 2. This would be 400 times 5 fourths squared, which equals 400 times, if we do 1.2 squared, that equals 1.44. And 400 times 1.44 equals 576. Next, we could try after 3 years. That's going to be 400 times 5 fourths cubed, which equals 400 times, now we have 1.2 cubed, which equals 1.728. Which equals 691. Point 2. So we want to know when it will reach 700. After 3 years, it had not yet reached it, but it would reach it in 4 years. So 4 years would be the answer. A new bicycle sells for $300. It is on sale for 1/4 off the regular price. Select all the expressions that represent the sale price of the bicycle in dollars. So if we look at A, we have the original price times the discount. This gives us the discount, not the sale price. B has 300 times 3/4. This multiplies the original price by the proportion that you would still have to pay. So this would give us the sale price, which is what we want. So B is a correct answer. C gives us 300, which is the original price, times 1 minus 1/4. What this is showing, 1 would be the full sale price, minus 1/4, which would be the discount. This would leave us with 3/4, which we just said in B would give us the sale price. So C also gives us the sale price and is a correct representation. In D, we have 300 minus 1/4. This is wrong because it is subtracting 1/4 instead of multiplying by 1/4 to give us the discount. So D would not give us anything. This represents nothing. It is not a correct representation of any portion of this word problem. And finally, E, we have 300 minus 1/4 times 300. Because of our order of operations, we would do the multiplication first. And we've already shown that 300 times 1/4 is the discount. So if we take the original $300 price and we subtract the discount, what's left is the sale price. So on this problem, B, C, and E all correctly represent the sale price in different ways. A computer costs $800. It loses 1/4 of its value every year after it is purchased. Number 1, complete the table to show the value of the computer at the listed times. So at 0 years, it is the original value of the computer, 800. After 1 year, it's going to lose 1/4 of its value, which means it keeps 3/4 of its value. And 3/4 of 800 is 600. Now we go another year. It loses 1/4 of its value, but keeps 3/4 of its value. And that would be $450. We go another year. It's going to keep 3/4 of its value. So we're going to multiply 450 times 0.75, which is $337.50. So if we are writing a generic expression, we would say to find t, we would have the original value times the proportion that it's keeping, which is 3/4, to the power of t, which would be the number of years. Number 2. Write an equation representing the value v of the computer t years after it is purchased. So for number 2, we're going to say v of t equals the original price of 800 times the value that it maintains, which is the factor 3/4, to the power of t, which is the number of years. And number 3, use your equation to find v when t is 5. What does this value of v mean? So we are looking for v of 5. That's 800 times 3/4 to the power of 5. That equals 800 times 3/4 is equal to 0.75. We're going to take that to the power of 5, and that equals 0.24. We'll round it there. Now 800 times that equals $189.84. This means after 5 years, the computer has a value of $189.84. A piece of paper is folded into thirds multiple times. The area A of the piece of paper in square inches after n folds is A equals 90 times 1/3 to the power of n. Number 1. What is the value of A when n equals 0? What does this mean in this situation? Well, n is the number of folds. And if you have 0 folds, then you are still at the original area of the paper. And in this case, that was 90. So A of 0 equals 90. And that means the original area is 90 square inches. Number 2. How many folds are needed before the area is less than 1 square inch? So we could make a little table out here. After 0 folds, it's 90 square inches. After 1 fold, 1/3 to the first power is 1/3, and 1/3 times 90 is 30. After 2 folds, that's 1/3 squared, which is 1/9, and 1/9 times 90 is 10. You can see that every time we fold the paper, we end up dividing the area by 3. So if we go to a third fold, that's 10 divided by 3 is 3.3. If we fold a fourth time, then we divide by 3 again, and we're at 1.1. So now if we go to a fifth fold, and we divide by 3 again, now we're at 0.4. Therefore, it takes 5 folds. And number 3, the area of another piece of paper in square inches after n folds is given by b equals 100 times 1/2 to the power of n. What do the numbers 100 and 1/2 mean in this situation? In this situation, 100 is the starting area of the paper in square inches. 1/2 is the factor. 1/2 is the remaining proportion of the area after each fold. So this says we're taking a piece of paper that is 100 square inches and we're folding it in half. And then we're folding it in half again. And every time we fold it in half. That's what a factor of 1/2 represents. At the beginning of April, a colony of ants has a population of 5,000. The colony decreases by 1/5 during April. Write an expression for the ant population at the end of April. So, we are starting with 5,000. Our factor is the amount that remains. So if it decreases by 1/5, it is keeping 4/5. And this is after only 1 month, so the exponent would be 1. Number 2. During May, the colony decreases again by 1/5 of its size. Write an expression for the ant population at the end of May. So again, we will start with our original population of 5,000. We will multiply by the factor, which is the remaining amount, 4/5, and the exponent will now be 2 because it's now been 2 months, April and May. And number 3, the colony continues to decrease by 1/5 of its size each month. Write an expression for the ant population after 6 months. We start with the original population of 5,000 ants. We multiply by the factor, which is the remaining proportion. If it loses 1/5, then the remaining factor is 4/5. And if it's been 6 months, the exponent is 6. You write exponential functions this same way every time. Lynn has 13 mystery novels. Each month, she gets 2 more. Select all expressions that represent the total number of Lynn's mystery novels after 3 months. So if we think about it, she starts with 13, then she adds 2 the first month, 2 the second month, and 2 the third month. So this is a linear function, and it matches choice A. Choice B is incorrect because this would represent an exponential function. Choice C would also represent the exponential function, and we have a linear function. Choice D simply adds together 2 plus 2 plus 2 and turns it into 6. So D is also a correct answer. And then E simply adds 13 plus 6 and turns it into 19. So choices A, D, and E are all correct representations of Lynn's mystery novels after 3 months. An odometer is the part of a car's dashboard that shows the number of miles a car has traveled in its lifetime. Before a road trip, a car odometer reads 15,000 miles. During the trip, the car travels 65 miles per hour. Complete the table. So before they start the trip, the odometer reads 15,000 miles. After an hour, we add another 65 miles, and we're at 15,065. Then we add another 65, and we're at 15,130. We drive another hour, we add another 65 miles, we're at 15,195. We drive a fourth hour, we add another 65, and we're at 15,260 miles. And finally, we drive a fifth hour, we add another 65 miles, and we're at 15,325 miles. Number 2. What do you notice about the differences of the odometer readings each hour? The differences are changing by adding 65 each hour. This is a linear function because we're adding the same amount each time. Number 3. If the odometer reads n miles at a particular hour, what will it read 1 hour later? Well, if it reads n hours at any time, 1 hour later, it will read n plus 65. That's because this is a linear function that adds 65 each hour. Select all expressions that are equivalent to 3 to the power of 8. Well, A is not correct because this swapped the base and the exponent. B has 3 to the 10th divided by 3 squared. When we divide with the same base, we subtract the exponents. So this becomes 3 to the 10 minus 2, which equals 3 to the 8th, and that matches what we're looking for. So B is a correct answer. C is incorrect because it turned this into multiplication instead of an exponent. D is correct because 3 to the 4th raised to the second power, if we raise an exponent to an exponent, we multiply the exponents together. So this becomes 3 to the 4 times 2, and 4 times 2 is 8. So we have 3 to the 8th power, which is what we're looking for. Choice E. We have 3 times 3 to the 4th power. This is the same as 3 to the 4th power times 3 to the 4th power. And when we multiply the same base, we add the exponents together. So this becomes 3 to the 4 plus 4, which equals 3 to the 8th, and that's what we're looking for. So E is also correct. And our last example, F, is 1 over 3 to the negative 8. Well, a negative exponent symbolizes 1 over, or the inverse. So this becomes 1 over 3 to the 8th. And if we have 1 over 3 to the 8th, dividing by a fraction is the same as multiplying by its inverse. And this just becomes 1 times 3 to the 8th, which equals 3 to the 8th. And that's exactly what we were looking for. So choices B, D, E, and F are all equivalent to 3 to the 8th power.